Sorry for the wait. Our next speaker is Alejandro from Chalmers Technology. And he will talk about sensitivity by parametricity.
All right, thanks. Sorry for the delay. So this talk is in the context of data privacy, specifically on differential privacy. Differential privacy is a new golden standard for data privacy, and let me give you a quick intuition. We have a data set with personal information. You can imagine that every row belongs to someone's private information. We run a randomized query and we get a result. Differential privacy says that if you choose any of the people in the data set and you remove it, and you run again the randomized query, you will get a result. The probability to get the same result as when you run it with the first data set is pretty close. It's like, and that closeness is related by this parameter epsilon. And in that way, the system cannot behave almost similar if in the dataset D1 and D2. Therefore, we are protecting the privacy of any individual. This is kind of the intuition. But how do we create these randomized queries? Well, I will show you one way to do it, which is called the Laplace mechanism. And it's like to create a randomized query, just get a normal query, like this one, how many people earns more than 60K, and just add some noise. So you get the result of the original query, and you add some noise. And the noise is drawn from the Laplace distribution, centered in 0, with an scale sensitivity over epsilon. The scale is what tells you how pointy the Laplace distribution is. Sensitivity is how much, if I change the input of the query, how much the output changes. And most of the differential privacy systems, they have baked-in queries, type of queries, with the corresponding sensitivity, right? That's okay. That's okay, but it has a limited the type of analysis you can do. In this work, the motivation is like we want users to write queries and automatically compute the sensitivity, so therefore being more expressive. And let me be more formal now, what I mean by sensitivity. And this is a definition we're going to use. We have a function that goes from A to B, so we have two metric spaces with distance functions in A and B. And we say that a function is k-sensitive if the input distance is at most n, the output distance is at most k times n. Okay? So that means that the output might increase the input distance at most by k. This is what it says. All right, are you warm up for this? Okay, let's see this function. This function is add 42 that takes x and just add 42 to it. And the specs metric is integers and the distance between integers. What is the sensitivity of that function? All right, let's run one test. Yeah, we say like we provide the input 10 and 11, they're at distance 1, the output is at 52, 53, right? So the output is at distance 1. So the sensitivity, therefore, is 1. So there are some more examples there. There is another example, for example, twice. This like multiply x by 2. And if we try this, the sensitivity here is going to be a little bit different. It's going to be 2. You can see here, for example, you give the input 10 and 11 is distance 1, and the output is 20 and 22. The distance is 2. Okay, so increases the input distance by a factor of 2. Okay, the sensitivity therefore is 2. Right, these are pretty simple functions, right? What about these ones? Sort, map, sum, append. What is the sensitivity of these functions? That's a complicated thing, right? And the question is like, can we compute in an automatic way the sensitivity of these functions? And the answer is yes, we can. But you can use the system called Fuzz, which is kind of the pioneer system in this area, where you can write functions and check for the sensitivity of them. But then you need to embrace linear types, sometimes dependent linear types, sometimes modal types. And they're very complicated concepts, at least for myself, for me, right? So the message on this talk is like, you don't need any of that. I'm going to show you how to do this, write user-defined functions, and automatically compute the sensitivity, right? Just using two things. Parametric polymorphism, so having for alls in your types, and having type constraints, which is type constraint is a way to restrict the for all. When you say for all A, it's not any type A, it's any type A that fulfills certain conditions, okay? And this is the main idea of the paper. It's like, let's do distance calculations at the type level. This is kind of the main idea. And for that, we're going to introduce this type called rel, that when you see something of type rel d of A, it means you should think as I having two values, that they are at distance almost d. Okay? Once you have that, then we can start writing functions using this type. For example, this add 42 that I showed before. Now we can write it using the rel type. And you can see here that add 42 goes from rel d of int to rel d of int. And it uses some special symbols here, because to construct programs with the type rel, you need a domain-specific language. And this is called Spar. And this is the interface. The thing I want to show you here is like two things. It's like you see that there are some calculations at the type level about distances, right? And here, to be technically precise, we have numbers, and then we have data structures like pairs and vectors. And when you start dealing with them, you need to start thinking about norms, like vector norms, to compute distances, right? And what I'm showing here is using only the L1 norm, which is defined like this. If you don't know about it, doesn't matter, just to be precise. But we support other norms. Yeah, and this is kind of the inside. We introduce a type synonym that says a function has sensitivity k, a function that goes from A to B. If the function, you can type it like that. It takes a rel d of A and returns rel k times d of B for all d. That's where the parametricity comes into play. If you can type check a function like that, it has sensitivity k. And you can see the formal definition that I gave you and the type that you see there are pretty close. Okay? This is the main insight. This is where parametricity comes into play. All right. So for example, the function that we wrote before, this is the type. If we use the type synonym now and type checks, has sensitivity 1. Okay? Yeah, and this was the question I gave you before, the sensitivity of these advanced functions, right? And then you can see then that source has sensitivity 1. These are functions working on vectors of fixed length, okay? Map has sensitivity k, the function that you're mapping on has sensitivity k, and so on and so forth. All right, let me connect this back to differential privacy, because we started with differential privacy. So this is implementation of the Laplace mechanism. This mechanism I show you that generates queries that fulfill differential privacy. And here we can see that this function takes data sets which differ in one row. It's at distance 1. Right? It takes a function with sensitivity sen, a function that goes from the data set and generates a number. And it produces a differential privacy query which we assert on given epsilon. Here the epsilon is not that standard, because epsilon could be any real number, but Haskell doesn't have, at the type level, doesn't deal with real numbers, so we are using fractions, rationals, okay? So it's a small detail. All right, so what advantages and limitations do we have? We support different metrics. I show you that if we deal with complex data structure like pairs and vectors, you need to choose norms. I use L1 norm, but there's another one called L infinite, and we can support it. We cannot support L2 norm, because for the L2 norm, if you're familiar with that, you need to do a square root and a power of 2. And the Haskell system is not strong enough for that. We implement advanced non-trivial differential privacy algorithms, like CDF, histograms, or k-means. It's not my intention to you understand the type signature, right? But it's just to give you a feeling that the things that we can write using our technique. And on top of that, we can compute the sensitivity of advanced functions, generic advanced functions like false, right? Where the fall is like, you fall over a list with a function with an arbitrary sensitivity, okay? Things that Fuzz cannot support, but DFuzz does. DFuzz is a dependent version of Fuzz. Yeah. And we implement all of that in 500 lines of code. Okay? Okay, this is great, but is it sound? Why we just like just hacking? And for that, in the paper you can find the formalization of the DSL Spar, we call lambda Spar. It's a model of the DSL. And we have types. We model the types in the calculus. Then we give semantics to a language based on logical relation. And then we prove the fundamental lemma of logical relations. And then finally, using that lemma, we show that if a function has the type for all d, rel d of A into rel k times d of B, has sensitivity k. Okay? So, all right. Some related work. So, you know, the initial motivation for this work was the work of Fuzz. So we encode all the examples that Fuzz does to compute sensitivity of functions. We encode it in Spar. And then the closest word to us is Solo from OOPSLA 2022, while they use polymorphism to compute sensitivity, right? And you will say, well, but I mean, yeah, you are doing the same thing. Well, not quite, because we use polymorphism in a different way. Yeah, you can see some difference there. For example, they need to assume the sensitivity of any higher order function. I should show you that we compute the sensitivity of map, which is a higher order function, right? And one of the main differences is like their calculus for the guarantees is monomorphic, while ours support polymorphism, right? And actually, we found a bug in the fold primitive, which is the only primitive of recursion. Of course, we communicate with them, and then they are aware of this. All right. To wrap up, yeah, the main message for you is like you don't need to use linear types to compute sensitivity of functions. If you have parametricity, polymorphism, and type constraints, then you are fine. So you can implement this in mainstream functional languages like Haskell, right? Yeah. So we have good sets of expressivity. I show you that we have implements many of the examples of Fuzz, as well as we implement advanced differential privacy algorithms. Yeah, and what I'm really interested in is like the next step. Where do we go next? So we found like there are some limitations in the Haskell type system, but you know we have dependent types that they also enjoy parametricity properties, right? So what can we do there that we cannot do here, or what things can be more natural doing in a dependent type language that here we are suffering a little bit of doing, okay? So with that, I thank for your attention. There where you have the code, and I will be leaving after lunch. So if you want to chat more about this, just talk to Elisabet. Elisabet will be around here. Raise your hand. Yeah. So she will be here, and she will love to talk about this. Thank you very much.
Thanks. Thank you. I really like the talk. So I don't work on types, but my understanding is that like this Lipschitz continuity stuff is like a hyper property, but then you denote the signature of your functions as like rel d to rel d. But the rel d things, like, I mean, that's not describing like the object that the function acts on. It's describing like sort of if you were to lift it over a pair, what would happen. So maybe
that's right. Yeah.
Yeah. So I guess my question is like, in your opinion, then like, what is a type? Maybe that's a confused question, but I guess I was surprised to see things done this way. I don't work in types, so I don't know if it's standard, but I wonder if you could like tell us whether this has anything to tell us about like what a type is, because it seems like it's a somewhat like non-standard take.
Right. So in logical relation, you relate terms, right? So you relate always two terms. And usually those terms need to be equal when you are not in rel. When you are in rel, those two terms, the interpretation is like those two things can be different, but they need to be at a distance d, right? So this is kind of the mental interpretation.
Okay.
Right?
Yeah.
So you see it as a pair, even though there is no pair, but yeah, semantically it's like having a pair.
Okay. Yeah, I just thought that was interesting because I hadn't seen that done before. So
right.
Thank you. This was a really cool talk.
Yeah, thanks.
Hi, nice presentation. I was wondering about divergence. How do you deal with that? and what guarantees do you have?
Right. Yeah, so I didn't mention that. This is all, these are all guarantees for terminating programs, right? So usually people, what it does is like, okay, if I diverge, distance is infinite, so the definition holds. But we don't like that approach, so we say, because it's like cheating a little bit, in my opinion. But what we do instead, we say like, all the guarantees are for terminating programs. And the DSL, yeah, you need to be sure that, because it's an embedded DSL, that you don't use any pure functions in Haskell that loop forever, right? So you need to be aware of that. Yeah.
Thank you.
Okay, because we're a bit over time, so let's thank the speaker again.